In this lesson we're going to look at how electricity is transported from a power station to your home. Okay, so we're using this symbolic diagram to describe the various processes or steps involved, okay, from the power station to your home. Okay, here at the other end of the diagram. And this power station might be, for example, a fossil fuel power station or a nuclear power station. Okay, so the job of the power station, if it's a fossil fuel power station, for example, will be to convert, first of all, chemical energy stored in coal, oil or natural gas into heat, and that will take place in the furnace of the power station. Or if it's a nuclear power station, then it will be to change nuclear energy into heat, and that will take place in the reactor of the power station. What we're really interested in is obtaining the heat, and then we're going to use that heat to, for example, heat up water to produce steam, and that steam or gas will then be used to drive either a gas turbine or a steam turbine, and then the turbine is connected directly to the alternator, which is the fancy name for the AC generator involved in power stations. As you know, it's like a giant dynamo, and it converts movement energy into electrical energy. And if you want to have a look at how an alternator works, then go to one of the previous lessons in this unit, and you can learn how it functions. Okay, so we've got the AC generator, and that AC generator will be, in most power stations, this alternator is rotating at a rate of 50 cycles per second, so it will be generating 50 Hertz AC current. Now, the voltage produced by a typical alternator in a power station might be something like about 25,000 volts. So I'm going to write down the voltage in red. All right, 25,000 volts, and what we've got to do then is this voltage, although it appears to be very high, but it's a bit low really to transport electrical energy. So what needs to be done here is to increase the voltage at which the electricity is transported from the power station across the country to the towns and then eventually to your home. So to do that, we're going to use a step-up transformer, and these are going to step the voltage up from typically from 25,000 volts right up to 400,000 volts. So as electricity is carried across the country, it is done so at a much higher voltage of 400,000 volts. Let's just remind ourselves how the step-up transformer works, how this works. And you'll remember that you've got the primary coil and the secondary coil, and they're joined by a soft iron core. That's a magnetically soft material which conducts the magnetic field from the primary through to the secondary coil and enables the transport of electrical energy from the power station to the transmission lines. Okay, so the secondary coil will be connected directly to the transmission lines that's going across the country. The primary coil will be connected directly to the AC generator in the power station. So remember that with these soft iron cores, they're magnetically very soft materials, so they are virtually 100% efficient. That's to say, virtually all of the electrical energy that comes out of the alternator and into this primary coil is transferred into the secondary coil and away along the transmission line. So we can say that the power in is equal to power out. That's assuming again that the transformer is 100% efficient, which it very nearly is. What does that mean then? If we've got the input voltage Vp and the input current Ip, and then we've got the output voltage Vs and the output current Is, then we can say that Vp times Vi is equal to Vs, voltage out, times Is, the current out. So going back to our transmission line diagram, what is really important in the transmission of electricity is that this voltage is as high as possible, and that will reduce energy losses in the transmission line. So it's important to have a very high voltage. Let's just make a note of that. Lower energy losses at high voltage, lower current. How does this work? Let's just plug these figures into our transformer equation. So therefore, if we've got an input voltage of 25,000 volts and we're using a step-up transformer to produce an output voltage of 400,000 volts, let's just say we've got a current of 800 amps being produced. by the AC generator. Then plugging these values into our equation, we can say that the power in, which is 25,000 times 800, must also equal the power out. Well, we've upped the voltage to 400,000 volts, then that means we must down the current to 50 amps. Okay, so although using the step-up transformer we've increased the voltage by a factor of 16, at the same time we've decreased the current by a factor of 16. 25,000 times 800 is equal to 400,000 times 50. The energy out is still equal to the energy in. Nothing's changed in terms of energy. The only thing that's happened is that the voltage has been increased, and having a high voltage but a low current will make considerable savings in energy losses as the electricity is transmitted along transmission lines. So once the electricity's got to where it's got to go, to the towns, to our cities, away across the country, then what's going to happen is that this voltage has got to be stepped down. So there's going to be a series of what we call step down transformers rather than step up transformers. So our first step down transformers here, I'll just write step down there, I won't write the word transformer just to save time. And for example, that will step down this voltage to say 33,000 volts. Now that's the sort of voltage that would be required, for example, for factories, for industrial zones in cities where still high voltages are required in order to operate equipment. Okay, so this step down transformer will serve for that purpose, but if we want to get electricity to our home, then we've got to use another step down here to step the voltage down from 33,000 to the standard voltage which goes into your homes, which is 230 volts AC. And so there we have another step down transformer.